Welcome back. At this point in the course, we've, believe it or not, covered the core computational machinery that you need to know to be a Python programmer. There's lots to learn. There's a lot of data structures and algorithms, but in terms of functions, variables, looping constructs, while and for, conditional statements, if, else statements, that forms the core of the programming language that you need to know to be a general purpose Python programmer. And again, lots more to learn, refining, honing those skills, writing good, efficient, well-documented, smart code will come with experience. But that's the core of it. Now, we're going to just, before we get into some more of the data structures and algorithms and what is called object-oriented programming, I want to just take a little breath and talk about something called recursion. And recursion, in my opinion, is this very beautiful computational construct. And it's particularly beautiful because it deviates from everything we have seen up until now in the way you think about the nature of computation. So again, everything we've been thinking about and everything we've been doing up until now has been functions, variables, looping, and conditionals. And recursion brings in this very nice and elegant and beautiful way of thinking about the nature of computation. And we're going to spend a little time talking about that because I think it's an important construct to understand as a general purpose computer scientist and programmer and data scientist. All right, let me start by reminding you of the definition of the factorial operator. So of course the factorial operator is denoted with an exclamation mark and it has the following definition. It is defined, as you can see here, only on positive integers that are greater than or equal to 0. And so the definition of factorial says that if n is 0, you're trying to, of course, compute n factorial, then n factorial is equal to 1. So 0 factorial is 1. And for all integers greater than 0, n factorial is defined to be n times n minus 1 times n minus 2 down to 1. That is the product of all of the positive integers from n down until 1. And of course, we've seen this before. We see it pops up in set theory and in probability and in counting all the time, standard mathematical operator. Right. So before we dig into the recursion that I want to be the topic of this set of lectures, let's just by way of practice write some Python code to compute this. And if you want to, you can pause the video now. This is a good little exercise, but if not, let's just go ahead and do it together. I'm going to write a function called factorial that takes as input an n. Now, let me just say before I dig into the code here, really, I should have some code in here that says, make sure n is an integer, make sure it's greater than 0. I don't typically do that in these little examples because it just creates a lot of code. But generally speaking, when you have functions like this that have constraints on the input, you should put checks and balances in your code to make sure that what is being passed in from the outside world conforms to your expectation. But again, just for cleanliness, I won't do this here. This code is going to compute factorial. We'll go through this step by step in a second. And you can see at the very end, it returns. And again, remember what return does. It sends it back to the calling function. And this distinction between return and, for example, print is important. It has never been more important than when we are about to start talking about recursion in a few minutes. All right, until then, let's go ahead and look at this code and make sure we understand it. So fact, of course, you can see here is going to be the variable that I send back. I apologize, they should both be color-coded the same. I initialize that to be 1. That's going to hold on to the running product. I is equal to 1 is a counter that is going to, as you can see in my loop here, while I is less than or equal to 1, is going to go from 1 to 2 to 3 to 4 up until n. I'm, of course, going to compute a running product. All right, here is my increment. I'll come back to this line in a second. Notice, by the way, I just want to introduce the shorthand. What do I want to do on each iteration of the while loop is I want to increment I by 1. I takes on the value 1, and then 2, and then 3, and then 4, and so on. This is a little shorthand because this is such a common expression. We say I plus equals 1, which simply means I equals I plus 1. So on each iteration, I'm incrementing I by 1. And what do I want to do? I want to keep a running product. So fact starts out as 1. I multiply it by 1. That's, of course, 1. Next time through, I have a 2. Multiply that product by 2. Next time through, multiply it by 3. Next time through, multiply by 4. And you can see I'm keeping a running product. fact is equal to the previous value of fact times the current value of I. I get through that whole body of the while loop, including n, of course, because n factorial is n times n minus 1 all the way down to 1, and then I return fact. One little point, by the way, notice that in the previous definition of factorial, I special case 0. Right? I said 0 factorial is 1, and then anything greater than 0 is this. I don't seem to have a special case here for 0, so let's make sure this works. Okay, so let's run through the code. N is 0, fact is 1, I is 1. While I is less than or equal to, while 1 is less than or equal to 0. Is that a value to true? No. So what happens? I pop out here, and what do I return? 1. That's 0 factorial. Nice little. I could have put a special case. I could have said if n equals 0, return 1, otherwise, but it just comes out because of the way factorial is defined in this iterative scheme here. Perfectly fine iterative scheme. Let's go through and just make sure we see how fact and I are incrementing, because that's going to lead us to where we want to go when we start talking about recursion. Let's say I want to call factorial with 5. So I want to compute 5 times 4 times 3 times 2 times 1. Good. First iteration through, first time through, fact is 1, I is 1. So I'm gonna do 2 columns here showing these values as I iterate. That Boolean expression, of course, evaluates to true. So I go into it, into the body of the while loop, and what do? I say fact equals fact times I. So what is fact going to be? 1. And what is I going to be? 2, because I incremented by 1 right there. Come back up, 2 is still less than or equal to 5. Dive back into the body of the while loop, please. Now fact is going to be the current value of fact times the current value of I. 1 times 2. Good. So fact is 2, increment I by 1. Go back up, Boolean expression is true. Multiply those 2, I get 6, increment. Let's do it again. Product of 6 and 4, 24, increment. Okay, now we got to start being a little careful because we're getting near the end. So I is 5. I come back up. Is 5 less than or equal to 5? Sure is. Come back in. Multiply those 2 values, of course, to get 120. Now increment I by 1. I come back up. 6 less than or equal to 5? No. Come back to the, get out of the body of the while loop, return fact, and I'm done. I've got 120. Okay, good. And you can see here that what we've done is on each iteration, we've computed exactly what we promised. This line is computing a running product. So by the time I get to the 5th iteration, I've multiplied 5 times 4 times 3 times 2 times 1. And when I was at this iteration, I multiplied 4 times 3 times 2 times 1, and so on and so forth. Now, there's something interesting looking at this iterative process, because what you notice here is that when I computed 5 factorial, along the way, I also computed 4 factorial, and along the way, I computed 3 factorial, 2 factorial, and 1 factorial. And that sort of makes sense if you think about the nature of the product. So what is n factorial? N times n minus 1 times n minus 2 down to 1. Well, what's n minus 1 factorial? N minus 1 times n minus 2 down to 1. And so to get n factorial, I sort of have to get up to n minus 1. And to get to n minus 1, I have to get up to n minus 2. And so I can sort of think about this definition slightly differently. I can define n factorial, or 5 factorial, let's say, to instantiate it as 5 times 4 factorial. And what is 4 factorial? Well, it's 4 times 3 factorial. And that sort of makes sense, right? Because it's 4 times the product of 3, 2, 1. Well, what's the product of 3, 2, 1? Well, it's 3 factorial. That's sort of interesting. So let me redefine this definition of factorial. So our initial definition of factorial was if n is 0, n factorial is 1. Good, easy. If n is greater than 0, then it's the running product of integers between n and 1. Okay. So let me take that insight that we just had from that iterative code and redefine factorial, here it is, recursively. Okay. And I'm going to tell you what I mean by recursively in a second. So typically speaking, recursive definitions have 2 components to it, a base case and a recursive case. And sometimes you can have more than one base case, by the way. So the base case stays the same. The simplest thing you can do is say, give me a 0 factorial, and I just tell you 1. There's nothing to compute. It's literally by definition. Yeah. For all other integers greater than 0, instead of defining n factorial to be n times n minus 1 times n minus 2 all the way down to 1, I'm going to define n factorial to be n times n minus 1 factorial, which let's start off by agreeing is absolutely 100%. Correct. Why? Because n minus 1 factorial is n minus 1 times n minus 2 per the previous definition. Okay, but imagine I didn't give you the previous definition. Imagine you didn't know what factorial was, and you came to me and said, hey, Professor Farid, what is n factorial? And I said, oh, it's really easy. If you ask me for 0 factorial, the answer is 1. And for all other values of n, n factorial is equal to n times n minus 1 factorial. You might say, well, okay, but what's n minus 1 factorial? And I'm like, oh, that's easy. That's n minus 1 times n minus 2 factorial. And you get the sense that I'm sort of screwing around with you a little bit because I'm sort of defining a function in terms of itself, and that is exactly what recursion means. But I am not, in fact, messing with you. In fact, this definition works. So let's see why. Let's say you ask me, what is 3 factorial? And I say it's 3 times 2 factorial. And so you've made a little bit of progress. You know it's 3 times something, but you don't know what that something is. And so you ask me, what's 2 factorial? And I tell you, well, it's 2 times 1 factorial. All right, we made a little bit more progress. What's 1 factorial? Oh, that's easy. It's 1 times 0 factorial. What's 0 factorial? Aha! The base case. 0 factorial is 1. And now what do you know? You know that 3 factorial is 3 times 2 times 1 times 1, the base case. And so it seems like this is sort of a weird definition because I'm defining a function in terms of itself. But eventually, if I follow down that road, because notice this problem's getting simpler and simpler by decrementing by 1, I will eventually get to the base case. And I will have built up an expression along the way. When you asked me for 3 factorial, I said it's 3 times 2 factorial, and then you went and figured out what 2 factorial was, and then you came back and said, it's 3 times that quantity. And then you did the same thing for 2 and for 1 and eventually for 0. And that is the nature of a recursive definition. And of course, we can now implement that in Python in very beautiful ways. So let's go ahead and do now a recursive versus an iterative. So I will refer to while and for loop implementations as iterative solutions because you're iterating. And what we're about to do are called recursive. And you'll see in a minute why there's a difference between these two and what that difference is. Please write a function, a recursive function, factorial, that takes a parameter n. Again, I won't check if the parameters are greater than or equal to 0. Base case is easy. If n is equal to 0, return 1. And notice here I'm going to now make the base case explicit. Okay, so this is easy and absolutely correct. Not a very useful function because for all other values of n, there's nothing to do. Now, what do I want to do if n is greater than 0? Well, if n is greater than 0, I want to compute n times n minus 1 factorial. Well, how do I compute n minus 1 factorial? I've got a function to do it. So what happens if I just say return n times factorial of n minus 1? There's the recursion. That function definition and that function call are the same thing. You are calling yourself recursively. Now also notice this return. I said earlier when we did the iterative solution, this is really, really, really important. And you're going to see in a minute why it's important. But notice I'm not printing, I'm not assigning, in fact, there's no variables here. There's no fact. There's no fact equals. I'm just building an expression, and we're going to see that in a minute. Put this into Python, and it will work. It will return for you 5 factorial, 10 factorial, whatever you want. And it seems sort of like we're cheating. It doesn't seem like it should work, but let's now, in fact, see why it works. And the magic here is that while it seems like all we're doing is calling this function over and over again, notice that we are building up an expression here. So I've peeled off, I've simplified the problem a little bit. I've said 3 factorial is 3 times something. What's that something? Well, go ahead and figure it out. And when you're done, come back and put it into this expression for me, and I'll tell you what the final answer is. So this little thing right here, this is it. And this returning of a value, that's where the nature of the computation is happening. And now you can see why recursion is so different. There's no variables, there's no assignment operator. You're building this expression up. And now let's make sure we can go and see that. And let's do that by calling 3 factorial. So here's my function definition. If n equals 0, return 1. Otherwise, return n times a recursive call to myself with n minus 1 as a parameter. I call 3 factorial. And now you've just got to follow the code. It's like everything we've done to now, just write out the code. What happens? Okay, 3 comes in. It's not equal to 0. So I come into the statement, and I return to the user 3 times factorial 2. But I can't quite return it to the user yet because that is not a value that I can compute multiplication on. So I have to go call factorial of 2. So it's sort of like if I said return 3 times square root of 27. I'd have to go compute square root of 27. It's not a recursive call. Come back, do the arithmetic, and then send it back to the user. It's the same thing here. The only difference is I'm calling myself, and I just have to remember that when I eventually get an answer here, I'm going to have to multiply it by 3, and that will eventually get sent back to the calling function. All right, so forget about 3 times for now. We'll keep a memory of that. Yeah, it's called a stack. Let's compute 2 factorial. That's what we need in order to finish this expression. All right, 2 comes into here. It's not 0, so we return what? 2 times 1 factorial. Okay, so we sort of got somewhere. We sort of didn't. Yeah. So 3 factorial needs to know the answer to 2 factorial. 2 factorial is 2 times something, but I don't know what that something is yet. So I gotta go figure that out, and then I'll eventually compute this, and then I'll eventually compute this. All right, let's go figure out 1 factorial. 1 factorial comes in, that's not true, so return 1 times 0 factorial. There it is right there. All right, now we're getting closer, right? Because what's going to happen when I call 0 factorial? 0 comes into here, and a 0, return 1. I have a value here. So this is going to go off and call something, and it's going to return an actual value. No more recursion. We hit the base case. No more recursive case. All right, now let's see what happens. Let's forget about the 3, forget about the 2 for a minute. Let's just look at 1 and below. Yeah. So 1 factorial is 1 times 0 factorial. 0 factorial is a function call, happens to be recursive, but honestly, I don't care. It returns 1. And so now that 1, and here it is, it's a return statement. Why does that matter? Because that's a function call. And that means I'm going to send a value into that function, and it has to send me something back that I can use in an expression. It's exactly like calling square root. You can't print the square root. That does me no good. I'm trying to use it in an expression. You have to return it to me, so that I can use it in an expression. All right, 1 gets popped back into this call for 0 factorial, and now I can do the arithmetic. I can do the multiplication. So I'm going to just multiply 1 times 1. And now I have an answer to 1 factorial because that evaluated to an actual value, and it's being returned back because of that return statement right there. So now the 1 gets replaced in there, and now I have 2 times 1 is the answer to 2 factorial. A 2 gets returned to that. The 2 gets returned to the factorial of 2, and now I have an expression that I can evaluate. So eventually, it took a little while, eventually what happened is that 2 factorial called 1 factorial, which called 0 factorial, which hit the base case, and then I started popping up those expressions, and now I have an expression, and I return, of course, 6. So the nature of recursion is that we build up expressions using a recursive definition of a function and these return statements which essentially hold the memory of that expression as it is being built. So you can see here it's a really, really different way of thinking about the nature of computation. It's not right or wrong, better or worse. Sometimes it's a little bit better, sometimes it's a little bit more elegant. Sometimes it's a little worse. Sometimes it's less efficient because you have to hold on to the memory of all of these things. But it's a really powerful concept, and I think it's an important way to think about the nature of computation. So we're going to spend a little bit of time looking at some more recursive examples and make sure that we understand this paradigm of computation, and we'll pick it up in a few minutes when we come back.